Nuclear fusion, the process used by the sun and stars to create energy, has long been the holy grail of the science world. Scientists realized in the 1920s, after the discovery of quantum mechanics, that our celestial companions were using fusion, not chemical combustion, to shine. This understanding marked the beginning of a century-long quest to mimic what happens naturally in the cosmos, within the constraints of Earth's laboratory settings. Fusion energy has since been heralded as the revolutionary, ultra-efficient power source of the future. This article explores the impact of fusion energy, along with its significance, potential benefits, and drawbacks. Fusion energy seeks to emulate the way stars create their power. It occurs when two light atomic nuclei combine to form one heavier nucleus, releasing a significant amount of energy in the process. The energy produced is much greater than that from conventional fossil fuels or even nuclear fission, as utilized in current nuclear plants. Fusion energy promises a future of unlimited, clean, and safe energy. It is effectively inexhaustible, as its fuel source is commonly found isotopes, such as hydrogen. This abundance contrasts with the finite nature of fossil fuels, and even the limited reserves of uranium for fission-based nuclear plants, providing a promising solution to future energy demands. One distinctive advantage of fusion energy is its environmental soundness. Unlike fossil fuels, fusion reaction doesn't produce carbon dioxide or other greenhouse gases, posing an answer to climate change. It also doesn't create long-lasting nuclear waste that makes fission-based nuclear energy controversial. The safety features of fusion energy encompass an absence of the risk of catastrophic accidents, such as those at Chernobyl and Fukushima. In a fusion reactor, a large-scale nuclear meltdown like those in fission reactors is impossible. If a malfunction occurs, the reaction naturally stops, and the small amount of fuel in use at any given time limits the potential radiological hazard. Despite the highly enthusiastic picture painted, fusion energy isn't without significant challenges and drawbacks. First, the technology to achieve and sustain controlled, net productive fusion reactions is still in the experimental stage. We are yet to witness a fusion reactor that produces more energy than it consumes. In addition, the development of functional fusion reactors requires substantial investment of time, effort, and funding, evidenced by the International Thermonuclear Experimental Reactor, ITER project. Initiated in 1985, this international scientific collaboration aims to prove the feasibility of fusion energy. However, it has faced massive budget overruns and delays, with the main plant completion now targeted for 2025, and operational fusion not expected until 2035. Moreover, issues concerning radioactive waste management persist. Contrary to some beliefs, fusion reactions do create radioactive waste, although less than fission reactors. The high-energy neutrons produced cause reactor materials to become radioactive, and managing this waste will pose challenges. In conclusion, the potential of fusion energy to solve pressing issues concerning energy demand, climate change, and energy security is immense, but considerable technical and logistical challenges must be overcome. Despite the substantial obstacles in implementing fusion energy on a large scale, it offers hope by providing a clear path towards a sustainable, safe, and carbon-free energy future if we continue to invest resources in its research and development. The history of fusion energy development tells us that while the journey may be long and fraught with difficulties, the potential reward makes it an investment that we cannot afford to ignore. This vision of a fusion-powered future opens the door to a world where the power of stars is within humanity's grasp, serving as the key to unlocking an unlimited clean energy source.